glad you made it back. Oh, we're having a ball here with Poisson's ratio. Alright, now I think maybe we gotta use Poisson's ratio in some sort of engineering problem, right? We can't just talk about the delicious properties of Poisson's ratio. We gotta actually use it to solve some engineering stuff. So go ahead, take a look at this example. As with pretty much every example in mechanics and materials, we need to take a second to go ahead and read through it. So we see here we have a tension test that's performed on a 0.5 meter long steel plate member having a cross-sectional area of 12.75 millimeters by 50.88 millimeters. Member is elastically loaded to a force of 222.4 kilonewtons and held constant. Here's a free body diagram of the plate with the forces applied at either end. You can see sort of the what's happening. We want to know what the elongation of the member is, all right? So that's what I sketched here in green, right? As we pull on this, the member is going to stretch in the axial direction, some amount, delta L, and delta L is the axial elongation of the member. Part B, we're going to talk about coming up with the reduced cross-sectional dimensions for the member. So let's start here with part A. Part A, we want to do the axial elongation. So let's think for a second, what formulas do we have to solve for delta L? Well, so far, the only formula that we've covered that has delta L in it is the formula for strain, right? So strain, we said, was epsilon equals delta L over L0. All right, so we could rewrite the strain equation in terms of delta L, and we would be able to say that delta L equals epsilon times L0. So we know L0. L0 is 500 millimeters or 0.5 meters, but we don't know the strain. And typically we think of strain as being final length minus initial length over initial length, but we don't have the final length. However, we had another relationship that involved strain, and we said in the linear elastic range, sigma was equal to Young's modulus times epsilon. So we had this relationship between stress and strain. And so if I rewrite this relationship in terms of the strain, I see that I can then plug that into my delta L formula, and I get that delta L will equal sigma divided by E in the linear elastic range, that's strain, times L0. Now, I'm not given any information about the stress either, but we recall that stress is equal to P over A. And so we have an applied force. We also have the dimensions for the cross-sectional area resisting the applied force. And so if I substitute P over A for sigma, I now have an equation for delta L in which I know everything, all the variables. So I'm going to just go ahead and rewrite this. Delta L is now P times L0 over E times A. And we're actually going to see this in the next lesson. We're going to call this Hooke's law. So we're going to see this equation again, and this will be one of the equations we use frequently when we talk about axial deflection. All right, so what are the variables that we have? Well, we know that L0 is 0.5 meters or 500 millimeters. I'm going to put all of these things in terms of units of newtons and meters. So I have L0 in meters. P is at 222.4 kilonewtons, which is 222,400 newtons. E is given to us as 200 gigapascals. Now, a gigapascal is 200 times 10 to the 9th pascals, and 1 pascal is a newton per meter squared. So this is what units I want to be in, so I can cancel out with the newtons and meters with my other variables. Finally, I need to figure out what A is. Now, A is the cross-sectional area that's resisting the force. So I imagine that force 222.4 kilonewtons, is being resisted by the shaded area that I sketched in place. So that shaded area is what I want to use for my value for A. That area is going to be 0.0127 meters. So make sure you have the units correct there. 12.7 millimeters, or 0.0127 meters, times 0.0508 meters. And if you want to go ahead and get a number for the cross-sectional area, you can. If we do the multiplication there, we see that the cross-sectional area is equal to 6.4516 times 10 to the minus 4 meters squared. Now to solve delta L, all we have to do is substitute the variables into this equation for delta L, and we'll obtain that delta L is equal to 0.0008618 meters, or that is 0.8618 millimeters. All right, so that solves the first part of our problem. So the next part asks us to calculate the reduced cross-sectional dimensions of the member under loading. So remember, as we stretch this rectangular member, we're going to expect that the cross-section is going to shrink in a little bit, right? So as I apply tension in the longitudinal direction, in the lateral direction, I would expect my rectangle to shrink a bit. And so we want to calculate the geometry of the shrunken cross-section due to this elastically applied load. All right, to do that, we're going to need Poisson's ratio. And Poisson's ratio tells us that nu equals negative strain in the lateral direction divided by the strain in the longitudinal direction. And in this particular problem, we're given that Poisson's ratio is 0.32. Now, I don't have any information on the lateral strain or longitudinal strain as of yet, but I just saw that in my process to calculate the axial elongation, I used the equation for strain, and this strain will represent our longitudinal strain. So we said that our longitudinal strain was equal to sigma divided by E. And so sigma, we said, was P over A, which is 222,400 newtons, divided by the cross-sectional area, 6.4516 times 10 to the minus 4 meters squared, all divided by E, which was 200 times 10 to the 9 pascals. So Newton per meter squared, that gives us pascals on the top and pascals on the bottom, so strain will be unitless. And when I do that calculation, I can determine that the longitudinal strain is 0.001724. All right, once I have the longitudinal strain and knowing Poisson's ratio for the material, and Poisson's ratio would be a material constant, so this is something you could almost, based on the material that you're using, you could look up this property in a table or in a material specification if you would need it to do your calculations. So the strain in the lateral direction is equal to negative Poisson's ratio times the strain in the longitudinal direction. So that's going to be a negative 0.32 times 0.001724. So doing the math there, I get that the lateral strain is going to be negative 0.0005516. Now remember, strain is unitless. If you like to think of this, you could think of this in terms of like meters per meter or millimeters per millimeter. And the negative sign just indicates in this case that in the lateral direction we'll have contraction or shrinkage of the cross-section. Okay, so that's all that the negative means. So because we had tension in the longitudinal direction, we have contraction in the lateral direction, or a shrinking of the cross-section. So I just want to graphically demonstrate what this is. So I'm sketching here a rectangle. This rectangle will be kind of our initial geometry, and then after we pull on the member in the cross-section is going to shrink in the lateral direction, both vertically and in the horizontal direction, as we're looking at the cross-section here in this view. To give some variables just to make speaking about it a little bit easier, I'm going to insert a XY axis. With this rectangular view, I'll say that Y is vertically upward and positive X will be to the right. And I'll center my origin for this box in the lower left-hand corner. All right, so if I want to figure out how much this member is going to shrink in the x direction, that'll be what I'll call epsilon x. And then I can also have epsilon y. That tells me the strain in the y direction. And both of these are equal to the lateral strain we just calculated. Now I have to come up with an expression for epsilon x. So epsilon is just change in length over initial length. So in the x direction, I'll say that this is basically like the change in the width of my plate divided by the initial width. So anytime we're dealing with strain, as long as we're taking a change in length and dividing it by the original length, that is our definition of strain. So I knew my initial length of 50.8 millimeters. That was my initial width. And I know my strain, the strain in the x direction, so I can calculate from this my delta W. This is now the change in width. And it's going to be negative because the width is getting smaller. Delta W in this case comes out to be negative 0.0280 millimeters. So hopefully you still have some room at the bottom of your page. I had to make a little bit more room to solve for epsilon y. Just like I did for epsilon x, epsilon y is just going to be now my change in my thickness divided by my original thickness, and I can set that equal to the lateral strain. And so my original thickness was 12.7 millimeters, so I can measure a change in thickness. 12.7 millimeters times negative 0.0005516 gives me a delta T equal to negative 0.007 millimeters. So a very, very small amount of change in thickness. Even my width, right, it was hundredths of a millimeter. That's barely perceptible. And this hopefully jives with our understanding of materials, right? We never look at steel members and, like, when we apply a load, look at them and say, wow, look how much it's shrinking, at least in the elastic region, right? We couldn't see, when we tested Stelia, we couldn't see the necking happen until we were well in the plastic region. So deflections occurring in the elastic region are very, very small. So let's go ahead and complete our calculations for the cross-sectional area. So our initial width of our plate was 50.8 millimeters. And our final width was 50.8 millimeters minus 0.0280 millimeters, giving us a resulting width of 50.772 millimeters. Likewise, we want to do the thickness. So our original thickness was 12.7 millimeters. And our final thickness was 12.7 millimeters minus 0.007 millimeters. And so that gives us a final thickness of 12.693 millimeters. So very small changes, probably not easily seen just visually that, our members are laterally shrinking or contracting as we apply a tension force in the elastic range. Now, we could look at this in the inelastic range. Just remember, though, that back when we were calculating strain, we assumed that the strain was equal to the stress divided by Young's modulus. So that only applies in the linear elastic region. So we would have to use the stress-strain curve information if we wanted to do calculations in the plastic range, because sigma equals E epsilon would no longer apply, so we'd have to do something differently there to get our value from our graph. Phew. Oh, this party's amazing. Hopefully I convinced you that Sigma Epsilon is the place to be. We got all the engineering stuff locked down, and that Tau Gamma, those people are just sheer losers. Stay away from their fraternity for sure. Rush Sigma Epsilon today!